Hi everyone, today we are looking at the concept of rate reaction in NCEA Level 2 Chemistry in the Achievement Standard 2.6, one of the externals that most schools do at the end of the year. Now the reason why I'm doing rate reaction for this particular recording, because I already done the exams for 2.4 and 2.5 from 2019, and rate reaction is something again that comes up every single year. It's normally a third of the topic, so you can expect to get 8 points out of 24 from doing rates reaction. And the good thing with rates reaction is that it comes from most of the concepts from year 11, and I will also do I'll do a recording that's more suitable for year 11s, so obviously we'll be more focusing on the year 12. So I'll be assuming that you know the basics, and I won't spend too much time on the year 11 stuff. Okay, but it's being repeated. That's why it's really annoying for us teachers to see students getting A3s and A4s, because you're missing out keywords, you're using wrong terminologies, and hopefully by the end of the video you can be more confident at this particular section of the exam paper. And as always, if you found the recording, if you found the video useful and helpful, subscribe. If you haven't, smash the like button, and we'll hopefully get the channel growing. Okay, so let's just start with something really basic. So the typical type of graph that you can see from rates reaction is that this is the amount of products. So sometimes they can put gas produced or whatever. It's normally the amount of products that's being produced, because what is the rate of reaction? The rate of reaction is how quickly a chemical reaction takes place. So if we break down the section to section A, B, and C, section A would have the greatest rate of reaction compared to section B, which has a greater rate of reaction compared to section C, which essentially is flat. So when it's flat, that means you're not producing any products over that period of time. I say, if you look at the section, there's no products produced, but time is still ticking. That means there's no more reaction. So this is something again from year 11. So you can a typical, like a merit-ish type of question, they would just ask you, all right, so what explain why the three sections, the rates reaction are different. So you just need to think about, with any chemical reaction, at the beginning you have all of the reactant particles readily available in the container, ready to react. So they're more likely to bump into each other. They're more likely to collide. They're more likely to collide at the correct orientation, and they're more likely to collide with sufficient amount of energy to overcome the activation energy, which initiate a chemical reaction. But as time ticks along, as time goes along, you will have less and less chemical reactant particles available, because they have already reacted. It is less likely for the remainder particles, the unfinished reactant particles, to find something to react. So as time goes on, the rates of reaction will decrease. At the end, there's no more collisions, no more colliding. You have no more products being produced. I mean, that's from year 11. Okay, so really basic stuff. When we show you the products on the side, when we say draw because sometimes we may ask you to draw a graph, this is what we expect you to draw. Okay, now the things that again affects the rates of reactions are these: concentration, surface area, what's the other one? Temperature. Just have a blind moment there. And so this is year 11, but in year 12 you also learn catalyst. Okay, so concentration and surface area are less likely to appear in year 12. They can show up, but they're not really at excellence level. Temperature is always the most difficult one, because you look at two factors here. Catalyst is year 12, and they may ask you to draw a graph to go with it, to show your understanding. Okay, so I'll go through both, all four of them, but I won't spend too much time on the first two. Okay, so first thing first, if we increase concentration, and I tend to show this to my students as well, which is a little flow chart, and then you can just fill in the words. Concentration. So when we increase concentration, what is the effect of increasing concentration? That means there are more reactant particles And something that we will prefer you to write in the exams, rather than just rote learn, just say more reactant particles. If they're more, like say for example, e.g., if I have 1 mole per liter of HCl versus 2 moles per liter of HCl in a different experiment, instead of saying more reactant particles, I'll probably say more HCl particles. Okay, just link to the question. They're quite a little bit picky on that with NCEA, but you know, you get the idea. But more reactant particles. Now, when we talk about concentration is moles divided by volume. So it's really important. You need to mention there are more reactant particles per unit volume. And people tend to get confused. What does it mean by per unit volume? You can say per liter, per mils. It doesn't matter. Per unit volume, it just means it doesn't matter what the unit is. If I set the unit to be the same, it doesn't matter what volume I decide. More concentration means there are more reactant particles in that certain volume. And I'll just give you an analogy on this. Like a lot of people ask, how much do teachers get paid? I'll say, oh, beginner secondary teacher gets paid about $48,000 a year, and a beginner engineer, I don't know, gets paid about $30 an hour. Then I'll normally ask my students, right, okay, so who earns more, $48,000 a year or $30 an hour? And they're like, how am I supposed to know? You know, to just look at me and think I'm crazy. You know, how am I supposed to make that comparison? Because how am I supposed to know how many hours an engineer works? Because the comparison unit is not the same. You're looking at per hour versus per annum. That's an obvious, that's not an adequate comparison. So this is what you need to understand. When we say there's more concentration, that means there's more reactant particles in the same amount of volume. Okay, so increased concentration means more reactant particles per unit volume. What does that mean? That means because there are more particles, they're more likely to collide. Okay, so because they're more likely to collide, therefore they're more frequent particle collision. Okay, so now depends on who taught you this. I prefer, I actually don't have a preference here. It's frequent means you have included the time already. So more frequent, higher frequency of collisions, more frequent collisions. That means this is equivalent to more particle or higher number, more particle collisions per unit time. Okay, so these two are the equivalent, and this is something they tend to look for, especially in year 11. In year 12, they do look for these as well. Okay, so you just need to understand, because it's more in concentration, there are more reactant particles per unit volume, therefore they're more likely to bump into each other, therefore there'll be more collisions. That's what it is. Therefore, there will be higher, there will be more effective, there will be more effective collision, which will have sufficient amount of activation energy, because this is kind of the emphasis in year 12. They'll have sufficient of energy, don't say force, okay, I'll get to that in a bit. They'll have sufficient amount of energy to overcome the activation energy, to overcome EA per unit time. Okay, so note I didn't say more frequent, I said there are more effective collisions which have sufficient amount of energy to overcome activation energy per unit time. So what does that mean? That means there is a higher rate of reaction. Okay, so this is kind of, I mean, they don't normally ask for concentration and surface area year 12 anymore, but you know, because it's a little bit too easy, it's just carried out exactly the same thing from year 11, so they tend to avoid it. Okay, so this is increasing concentration, and with flowcharts like this, hopefully that will make your life a little bit easier, because I can show you that if you can just memorize one, you can memorize the other one as well. So let's look at surface area. So I'm going to use the same flow chart. I'm going to cheat a bit. I'm going to recycle some of the things I've got here. So what does more surface area mean? So more surface area, so this is looking at powder versus chunks. Okay, so it's very obvious. So nothing else is changing. You just have more surface area. So what does that mean? That means more reactant particles. More reactant particles are exposed. So that means and readily available to collide. Available to collide. Okay, so what does that mean? That means it's going to be more likely to collide, more frequent particle collisions, and the same thing that we just went through again. So you just need to, once you get the idea, the rest is pretty straightforward. But then the key words, guys, more in concentration, we're looking at more reactant particles per unit volume, more particles exposed. And when I mark the school exams, I tend to see answers where people get really confused. They go, they think that chunks tend to have high surface area. You need to understand that. I always use this analogy. If you put a whole chicken into the oven versus sliced up chicken of the same size into the oven, obviously the sliced up ones will get cooked faster because it has more surface area. It can be heated much more easily compared to the whole chicken, which has a smaller surface area. Now, the key thing that you want to avoid, because we're really picky on the wording, the particles, the surface area is different, but the size of the particles don't change. It just means with a greater surface area in the form of powder, it just means you have more things exposed and they can collide and they can bump into each other, and then you have all of these following things. Okay, so you have more frequent particle occlusion, more particle occlusion per unit time. So you got more effective occlusion that will have sufficient amount of energy, sufficient amount of energy to overcome the activation energy per unit time, and therefore there's a higher rate of reaction. The key words, that's what we're looking for. And just something a little bit more, because they may ask you to do this, which is very likely. Let's do some graphing. So if we have the same graphs, this is products, this is time, they may ask you to label this on the graph. Let's say if this is 1 mole per liter HCl, and they ask you to draw 2 mole per liter HCl, like on the same graph, how would you draw this? It's typically this. You have more, well, don't make it that steep, but then you end up making more products because the two lines don't join together. Now that is assuming, it is an assumption that we don't really require a year 12 to understand. Some students have asked me before. I don't really want to confuse you. Just remember the basics, that if you increase the concentration of the ingredients, you have more stuff. It's kind of like if you can cook, if you know anything about cooking, you have more stuff to cook, then you obviously produce more things because you have more reagents at the beginning. Okay, so if we look at surface area, if we look at the products and then time on here, let's say if this is, let's say, chunk, how do I draw the powder? Well, if you draw the powder, it's going to look like this. It's going to look like that, and they finish at the same point because they have the same. So the green one will be the powder one because they have the same amount. Okay, so you need to look at they normally give it to you in a table. Look at the table. They should be really clear that they're only changing one thing, like say in this case powder versus chunk. Everything else should be the same. So it just means the powder will finish reacting faster, but you are still producing the same amount of stuff. Okay, so that's concentration and pressure, very straightforward. I do want to do temperature now because temperatures tend to be the hardest. Now if we do temperature, now temperature means two things. Temperature is always examined. I mean, I'm not saying it will be examined this year, but it has always been examined for the past 4 or 5 years because this is the most difficult idea. Okay, so if we increase temperature, because there's two folds in this part. If we increase temperature, what does that mean? That means the particles or the reactant particles have more kinetic energy. Okay, so they're more kinetic energy. So what does that mean? because it's transfer from heat. But if they're more kinetic energy, so the particles, they will move faster. What does that mean? They move faster. That means they're more likely to collide with each other. They're more likely to collide. So what does that mean? That means you have more frequent particle collision. And this is where people just keep going, yeah, higher rates of reaction, and then you wonder why you only get a merit, because you forgot the other part. Increased temperatures of the particles are more EK. So hopefully this makes sense. More kinetic energy, they move faster, they're more likely to collide, they're more frequent particle collisions. Okay, or you can say higher number of particle collision per unit time. But because they're more kinetic energy, a higher proportion of these collisions, because you're now colliding with more energy, will have sufficient amount of energy, to overcome EA, which is activation energy. Okay, so they're more likely to collide, and the a higher percentage, a higher proportion of these collisions will have sufficient amount of energy to collide, to overcome the activation energy. You can think of it as this example, like say, for example, let's just make this up. Let's say your left hand is a particle, your right hand is a particle, and they each have 20 kilojoules of energy. They collide, they generate 40 kilojoules of energy, but then the activation energy is 50 kilojoules. So if they collide, boom, yes, they did collide at the correct orientation, but they didn't meet the criteria of the 50 kilojoules, so there's no reaction. But at a higher temperature, so if your hands are going faster, they now have 50 kilojoules each, for example, and then they boom hit each other. Now you generate 100 kilojoules of energy, which will overcome the 50 kilojoules of activation energy that we had before. A very misconception that people have is that the activation energy is constant unless you put in a catalyst. Increasing temperature does not increase the activation energy. If you put that in, that is a big cross straight away. Okay, and activation energy, it is a barrier that's an activation energy. Like say if I do an exothermic reaction here, activation energy is this. It doesn't change unless you put a catalyst into that, which we'll talk about later. So changing temperature does not change activation energy. Okay, if you put that in, like I'll say that again because I've seen that so many times in our school exams, it will be marked as incorrect. Okay, now another thing that you need to understand is that these particles are colliding with more energy. I've read the marking schedule from NCEA. If you said force, you will be marked wrong. Okay, because at year 11 is okay, but as a year 12 chemist, you need to understand that force is more of a physics idea, whereas energy is that, they have more kinetic energy from the heat energy, so they are colliding with more energy to overcome the activation energy. Okay, so force is not appropriate at year 12. Okay, so when you think about force, no. If you think about temperature, like increasing temperature increases activation energy, no. Okay, don't just get that idea out of your head. That's not correct. So these two factors combine together, so the more frequent collision, a higher proportion of these collisions have sufficient amount of energy, therefore you have more effective collision per unit time, and therefore you have a higher rate of reaction. Okay, so this is twofold, and if you just do one part, a lot of people just do one part and then you normally get an M, and this is where it's really big shame. You have to understand it's two factors. One is that they're more likely to collide because they're moving faster. The other one is that they'll be colliding with more energy, which overcomes the activation energy, so a higher percentage of these collisions will have sufficient amount of energy. Okay, so that's temperature. Temperature is far more important compared to the other two, because if you don't believe me, print out the past 5 years exams, have a look at yourself. Okay, now next one, which is catalyst. Now catalyst is something that's really easy to spot. They will give you like say the questions, they have tables, and then yes, you see a random chemical that doesn't seem to be, you know, relevant, but then it speeds up the rate of reaction. So what does a catalyst do? A catalyst, it increases the rate of reaction. I'm just abbreviating here, rate of reaction, by providing an alternative pathway. Alternative, oh god, I can't spell tonight. Alternative pathway with lower activation energy requirement. Just activation energy, that's enough. Okay, and you can say it doesn't get consumed in the whole thing. You know, if you do biology as well, you can, you know, that links quite well with bio, like proteins and all that sort of stuff. But in chem, you just need to understand it provides an alternative pathway with a lower activation energy requirement, and this is a diagram that you're required to draw. Now, if you see the label as energy on the side, you can't draw the graph that we did previously, you know, the one that looks like that. That will be inappropriate to draw here because the axis title is energy. So how do we demonstrate activation energy? So this is from here to here, that is the original activation energy, and then from here to here, that is the new activation energy. Just mix up the colors. Okay, so this is the new activation energy. So what does a catalyst do? It does that. Therefore, more, again, this goes back to what we talked about for temperature. More occlusions will be effective or slash successful because there will be colliding, they will collide with enough energy to overcome the new EA, which is lower than original. Okay, so same thing again, so more effective occlusion per unit time, you know, the same stuff that we just talked about before. Okay, so this is something per unit time, higher rates of reaction. This is something that it's definitely worthwhile to spend some time to go through, because as you can see, very straightforward concept, but we're very picky on the wording. Okay, and so compared to some of the new stuff like say equilibrium, acids and bases, pH calculation, if you're not planning to do year 13 chem and you just want to pass, you know, rates of reaction for this particular standard, it will be your saving grace. Okay, so I will be definitely doing, I'll probably for year 12 videos, the next one I'll do is probably going to be on equilibrium and KC, looking at Le Chatelier's principles and all that. So that's something that you could look forward to. Okay, so like always, smash the like button, subscribe if you haven't, and I'll see you guys next time. Bye bye.